The logical effort model allows us to estimate the propagation delay through a single logic gate or a single logic stage as being comprised of two components. One is a fixed parasitic propagation delay, that is the intrinsic delay, that is the delay required to transition from a low to high or high to low on just the output pin of the logic gate without connected to any load. And there is a linearly increasing component called the extrinsic load, and that is the delay, the component of the delay that is due to charging the number of logic gates that are being driven by the output of the logic gate under question. And basically logical effort formalism allows us to see the trade-off of transistor sizes in managing the proportion of delay contributed by the intrinsic rise time or the extrinsic load rise time. So if you notice that if we increase the width, the W, so L is fixed in any process technology, but we have the option of increasing the width of the transistors of the logic gate. That means we actually have a larger size logic gate. The gate understudy, the RC component of the gate understudy, you increase W, you reduce the drive. If you increase W, you reduce the drive strength. So this reduces the drive strength, but you increase the capacitive load, the intrinsic capacitive load of the gate by the same amount. So increasing W does not change the propagation delay due to the intrinsic load, but it does change the propagation delay of the extrinsic load, because if you use a larger size gate to drive the same number of logic gates at the output, that larger size gate will be able to generate more current, and therefore it will be able to drive more logic gates at its output. Okay, so the logical effort formalism is just allowing us to use the transistor width as a design parameter in order to balance the component, the proportion of delay that is due to the intrinsic charging, and this is a proportion of delay that cannot be changed by width. There is a baseline delay here, but depending on the size of the logic gate under the design, we can actually choose to reduce the contribution of the extrinsic load. Now you may ask, why shouldn't we just size the logic gate to be a large size so that we make the propagation delay due to the extrinsic load to be zero? Well, it's for the simple reason that if you have too large a logic gate, this consumes a lot of area on the chip, so your device becomes larger, and it also consumes a lot of energy. So you're performing the same computation, and in order to achieve the greatest speed, that is to reduce the proportion of extrinsic load contribution, you would need to use greater amount of current and therefore expend greater energy in order to achieve this speed. So that logical effort, as you are now probably being able to intuit, we can use this idea of being able to balance the way that energy is used to allocate the delay, the proportion of the logic gate delay to the intrinsic versus the extrinsic load. So another way of saying it is that logical effort allows us to see that the delay of a logic gate, a single stage of a logic gate, there is a fixed intrinsic delay, that is the delay of rise and fall transitions of the logic gate itself, and there is an additional component of delay that is due to driving the loads at the output. And if we want to actually make the device faster, we pay the price of increasing the width of the logic gate under design in comparison to the width of the logic gates at being driven, and this comes at the price of power and space, but we're able to reduce the delay.